Good.
We already just talked about this. So what's Fibonacci sequence?
1, 1, 2, 3, 5, 8, 13, 21.
It's just making things up.
The next term is the sum of the previous two.
Right. So you start with the 1, you go to a 1 after that, you add these, the first and the second to get the third.
Cool, pay attention.
Second and third to get the fourth. Third and fourth to get the fifth, and so on.
34. 55. I don't know for that. 80 something.
That just looks like a double S.
Face is a good double S.
Ouch.
What about 89? Looks like an 8 with a football player.
Did you write 87 and then do a circle?
That's what it looks like.
I can't make your face joke, I have that.
Your face is like a 7 with a circle.
Okay. Have I bored you yet?
What was that?
Anyway. So Fibonacci sequence out 2 is the most terms I've ever seen written out 2. Anyway, the point is it's a recursive sequence, basically. So if you want to write it in math speak, it would be...
I'm trying to see what Fibonacci sequence was.
Here, it's spelled Fibonacci.
No, exactly.
The zoom function's really helpful.
Yeah.
Something you can't get with your iPod camera.
Yeah, I know. So, yeah, it's just saying you take the first term plus the second term to get the third, and second and third to get the fourth, so on and so forth. Starting with 1 and 1 is your first 2 terms. Anyway, so what's so special about this? Well, it was came up with a guy by the name of Fibonacci. Actually, I don't think that's his real name. I think it was something else, and he had the title Fibonacci, but I don't remember. Anyway, the special thing is if you take the ratio of one number to the next, 1 to 1, 2 to 1, 3 to 2, it bounces back and forth, gets bigger, then smaller, then bigger.
Is this an alternating series?
It's not an alternating series because it's not getting negative. What's that? 8/5?
No, what was it?
13 over 8 is 1
The
point.
difference between them is alternating.
See how it's getting closer
Yeah.
and closer to one certain number? And that number is roughly 1.618.
The residual is alternating. That's the word for
There
it.
we go. Good, Cameron.
That's all I learned in AP Stats for a semester.
That's all you will ever learn in AP Stats. So, you have this number that converges on, and we call that, by its Greek letter, phi, or phi, for fun. Anyway, the point is that this Greek letter actually makes it really complicated to figure out what way to pronounce it. Most Americans will tell you it's phi, spelled this way. Most Americans will tell you it's spelled phi. In the Greek alphabet, it's actually pronounced phi. But then again, that would also mean that we can pronounce this
As P?
as P. So, give or take, whatever you want to call it. I'm going to call it phi because it sounds more pompous and British.
BT?
Maybe you have seen, I'm not going to draw it on the board because it's going to be too complicated, but a golden spiral before.
Oh, yeah.
And what this does is that it takes the dimensions of the Fibonacci sequence up there and makes it the dimensions of rectangles. If I can find it. Clearly did not plan this out very well. Here it is. So, camera. I don't think you can see it very well. Here's
there
a
we
1
go.
by 1, then a 1 by 2, then a 2 by 3, and 3 by 5, 5 by 8, 8 by 13,
There you go.
13 by 21. And if you take, your face is 34. If you
That is like
draw-
your go-to insult, isn't
I
it?
don't have very many other immature remarks.
Totally understand.
It really
This isn't a very good curve.
perfect.
Anyway,
It's like a
this
9.
spiral is often called the golden spiral, and that is because the ratio of phi is often called the golden ratio, because it's been considered aesthetically pleasing in art in architecture and all sorts of different things.
How did you do this on the polar graph?
I don't know.
You should figure that out.
Actually, I was trying to figure that out. Other things you can,
Oh, that's
other representations of phi graphically is if you take 3 straight lines that are all length of 1, find the midpoint of this first one vertical, and make that. So this is 1, you go halfway through, and you make a line going down. Then you find the midpoint of that, and make a line going down. These are all the same length, theoretically. I didn't draw it very well. And this is going to be A. This point where it intersects is going to be B. This point is going to be G. A to G is the same in proportion to A to B. So this to this equals phi. Another ways to show it graphically.
That one's better because it doesn't have to, like, it's not a limit of something, it's just
Exactly.
that.
You have a circle, and you inscribe a triangle inside it. Find the midpoint of these 2 sides, and draw the line so it goes until the end. Once again, same ratio.
What?
Draw another circle.
Pentagon?
Pentagon inside. We're gonna do this. A, B, G. And if we don't draw the circle, just do a pentagon. Whoops.
Is Mrs. Yankus here?
She
Just
just
left a
left.
second ago.
Yeah.
Just left for the day, or, I mean, she,
I think she's coming back,
Yeah.
but I'm not certain.
There we go.
Okay, anyways, not regular at all, but we'll pretend it's regular.
Okay.
And it's going to be a length of 1 for the sides, right? So take a guess at what this length is going to be.
A to G.
Yep.
Oh.
That's going to be phi.
Hmm.
And take a guess at what length this is going to be.
A to B.
1 over phi. So, again,
So
Phi-
phi's reciprocal.
yeah,
Interesting.
phi's reciprocal. You can also do it. Anyway, so these are kind of start to show you how this golden ratio that kind of got made up by Fibonacci somehow pops up everywhere. By everywhere, I mean everywhere. For example, take a look at your next time you see a pine cone, pick it up and count the number of spirals there are from the bottom, and there will most likely be a Fibonacci number of spirals going both directions. You can do the same thing with pineapples. You can do the same thing with sunflowers. Pretty much a bunch of different things that have spirals on them. You can count them. Same thing with artichokes and flowers and all sorts of crazy things like that.
Huh.
And if you're curious why, see the link down below, which you guys can't see because you're in real life. Sucks to be you.
Dang it. Lucky YouTube.
Yep. Oh yeah, so how are we going to actually get phi? One of the interesting things about it is that it has this weird property of that phi squared equals phi plus 1. This is like 2.61, and this is 1.61, roughly.
Weird.
Which makes it even weirder if you think about it this way. Phi equals phi to the first plus phi to the 0th. Because anything to the 0 power is 1.
Yeah.
What?
So that is really strange, isn't it? In
Huh.
fact, if you wanted to get even weirder, phi to any n plus 2 power equals phi to the n,
No way.
oh sorry, n plus 1, plus phi to the n, anything. It's really weird.
Whoa.
And this, if that looks familiar, it's because it's just like the Fibonacci sequence it just came from. If you add 1 phi power phi to the next power phi, you get the next one. Whoa. Exciting. So, for example, like we said, 1 plus 1.618 is 2.618, which is the second power. If you add the first power and first power, you get 4.236, which is the third power. Second and the third gets you the fourth power, and so on and so forth. So let us say that we want to solve for phi instead. We'll look back in here.
And you can use the computer now.
Oh, thank you.
Do you have to use the internet or just the?
Maybe.
Yeah, probably the internet.
We love the internet.
I will call it up for you.
Okay.
Slow computer.
So if we pretend this is just like, these are like x's, and we're trying to solve for x, then we could say x squared equals x plus 1. And that reduces to x squared minus x minus 1 equals 0. And the solution to that equation is your ultimate number of how they get phi. Not as elegant as pi, but still very clean compared to a lot of things. For example, another way you could represent phi, we've done this as a riddle,
Oh. Yeah.
is 1 plus 1 over 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 1 plus forever and ever and ever. We put this in a math club video before, and I'm not going to bother doing it again. So another way to do it, oh yeah, this equals phi. Phi also equals the square root of 1 plus the square root of 1 plus the square root of 1. This needs to be
Oh my
solved.
goodness.
Square root of 1 plus the square root of...
That was last week.
Yeah.
My goodness.
If that's not confusing enough.
Oh gosh.
So,
All the lines.
all the lines.
Even the ones in the addition signs.
Exactly. And phi and 5 seem to be as thick as thieves. They always seem to show up together. For example, here's 5. Here's another place it shows up. 5 to the 0.5 times 0.5 plus 0.5 equals phi.
What? How does somebody come up with that?
Who figured this out?
My goodness.
Phi to 0.5 times 0.5 plus 0.5 equals phi.
My goodness.
I don't know how they came up with that, but
Square root
That's-
5 over 2.
But 5 and phi like to hang out together. I think they just because they sound so similar. Anyway,
You can see it from there.
well, yeah, it's in
Yeah.
there, and maybe we can actually do a proof of why that happens.
Probably.
Speaking of rad 5, you can find any term of the Fibonacci sequence by rounding this. Well, wait, no. You can find the nth term of the Fibonacci sequence by taking the nth power of phi and dividing it by rad 5. So if you get raise phi to the third power and divide by rad 5, you get 1, 2, 3, you're going to get 2. Well, roughly 2. I think you have to round a little bit. What you don't have to round is if you take any power of phi minus 1 and divide it by phi power without the minus 1, that will give you a whole number. Which, if you know anything about irrational numbers, you rarely ever get to do that with pi.
Yeah.
So that's another freaky thing. And I think that has to go back to the whole phi equals this sort of thing.
Hey Ben, just shut the door when you guys finish.
Okay. And the other place it shows up is in Pascal's triangle. But I'm not going to go over that right now because I am running out of time on this video, I'm pretty sure. So anyway, cool.
Good catch.
We have, yeah, caught it with the ground. And so we have phi, and it just shows up everywhere, and it's just kind of like E for me. You know, my love obsession with E.
Yes.
But phi actually has a lot more places that it just shows up randomly. And not even randomly, because if you look at the video that I talked about earlier, done by Hart, she'll tell you that it wouldn't make sense for nature to actually be that random. It actually makes a lot of sense that it does follow things to do with D and to do with the Fibonacci numbers. It's not that math somehow mysteriously ends up being part of daily life. It's that daily life comes from math. And I think that's one of the most beautiful things that you can learn through this little irrational number that we don't even know how to pronounce.